Okay, friends. Yes.
Today, are we doing like the which bonds like broke on both sides and calculating it?
Yeah.
Oh,
Sort
I
of.
tried some yesterday. Like,
Oh, good. Good, good.
Huh? What the hell? Oh.
Ain't it standing on free cookie? Oh, he's good though. But they're like kind of. But they're still good.
So yesterday, it was expressed to me that everyone was a little bit confused about things, but it's okay because we're going to spend a little time with it today, and then you're going to have some work on it on your own time as well, so you can consult with each other and consult with me and just work on things a little bit, okay? So we're going to start by taking a look at these bond enthalpy calculations because I was just going to get some extra practice problems, but then I found this and I'm like, this is pretty good. So I, stole it and, got it ready for you guys. So bond enthalpy calculations. Hi. So
Good afternoon, everyone. In a few
Oh,
minutes,
yeah.
we'll be conducting an earthquake drill.
What?
The ethanol teachers, please read.
It's okay. We don't have to like exit the building this time.
The drill will start in a few minutes.
Okay.
We will not be evacuating.
Pardon me?
Oh, the fire drill today. At least that's my friend.
Oh, yeah. No, we're not exiting the building today. We just have to get under the desks. Okay? And they make it shake.
I thought it was period 2.
It used to be period 2, but period 2 got hit twice already with like fire bells. And so we're spreading the joy a little bit so that it doesn't always have to be period 2. Okay. So when chemical bonds are broken, and I thought of something yesterday that might help you to remember. Okay. Have you ever heard of like the crime breaking and entering? If you haven't, this might not help you, but breaking and entering. So when we break bonds, that is endothermic. Breaking and entering. Ah, yes. If you've never heard of breaking and entering, this might not help you. But what happens to the thief's bank account once they have broken and entered? The thief's money, does it increase or decrease? Increases. Therefore, delta H is positive. Yes? You have to look at it from the thief's perspective. If you look at it from this perspective of, if you look at it from the perspective of the homeowner, then they're not very happy and their bank account goes down. But from the thief's perspective, it goes up. So if you don't understand why bond breaking is endothermic and why bond formation is exothermic, this might just at least help you remember, okay? Eventually, hopefully you will understand, but sometimes understanding takes a little while, right? So this might help you to remember. You can also remember that when I broke that, it took an input of energy, right? So that's the other way to remember bond breaking is endothermic. So bond breaking is always endothermic, bond making is always exothermic. And when we have a reaction, we are breaking the bonds in the reactants and we are forming bonds in the products. So our overall enthalpy changes. If we take our reactants and we break those bonds, and it requires this much energy. And then we end up with our products.
In the event that an earthquake occurs while at school, we need to practice and be prepared as a school community. If an earthquake happens, we need to immediately do the following. Drop to the floor, move away, and face away from windows and items that may fall. Cover yourself under a desk, table, or counter and cover your head. Hold on to the base of what is covering you and move with it until shaking stops. Listen for instructions to evacuate to a designated zone. Once the shaking stops, count 60 seconds out loud. After 60 seconds, you would need to evacuate the building. When we practice this drill, the signal to end the drill is the ringing of 5 bells. However, in a real earthquake, no one should re-enter the building. We will now begin the drill.
All right, everyone, under your desks.
Oh, that's the thing.
Here we go. Under your desk. Stop right there. Hold on. I have that. And now we start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44.
Thank you for participating in our earthquake drill.
What?
At this time, we ask that teachers debrief the post-drill discussion questions with your class. Thank you.
Okay, hang on, I gotta find these post-drill questions. Where is it? Earthquake. Earthquake. Ah, here we go. Okay. Question. How can you and your family practice and plan at home in case of an earthquake? Answer. Answers to this question may vary. There are some great resources to share with students found at the following website below, such as tips for how to secure your furnishings and home structure and 7 steps to earthquake safety. Do you guys know if your furniture has been secured to the walls? Okay, if you don't, like let's say you have a bookshelf in particular, because bookshelves are like tall and heavy and they can fall over, you need to make sure that it is actually secured to the wall, okay? And so for example, this little thing here will probably tell you how to secure your home furnishings and home structure. So you could go home to mom and dad and say, hey, mom and dad, I'll put the link on our team if you want to, okay? Probably most of you will just ignore me. But honestly, like if it were me, I probably would. I'd be like, Mom, Dad, have we? Because I'm like a little bit paranoid. I'm like, I do not want a bookshelf to fall on me. I don't want to be crushed under the bookshelf, right? And they have stuff here. So I'll stick this on our team. There we go. There's our team. And we'll just put it in the general channel. There we go. Earthquake info post. So you can go and ask your parents, and you can also ask them if they have an earthquake kit. My parents gave me an earthquake kit for my birthday a couple of years ago because I had not gotten around to making one. So that was quite nice. They're retired, so they have time to do this sort of thing. So that was quite nice. But if you're like, hey, Mom, Dad, what would I like for Christmas? I would like to not die if there's an earthquake. So could you please get us an earthquake kit? Okay, there you go. All right, that was it. All right, so we have our exothermic reaction where bonds made releases more energy than the bonds broken takes up. We have endothermic where the bonds broken requires more energy than the bonds made. Okay, and in that case, we start out lower and we finish higher, so the overall delta H is positive. Now, this next little bit is not going to be tested or quizzed by me, and it probably won't be tested or quizzed by, or it won't be tested on AP either. But it's kind of worthwhile mentioning because sometimes there are several ways to calculate the enthalpy of a reaction, the delta H of a reaction, and you'll get different values depending on which method you use. And in general, bond enthalpies tend to be one of the least accurate ways of calculating the enthalpy of a reaction. Okay, we'll learn some other ways later on. So why are they not so accurate? That's because every bond, when we calculate its energy, we are talking about an average bond energy, not all CH bonds, for example, are the same. So you can have a bond in a compound and it will either be stronger or weaker, in other words, require more or less energy to break, depending on what other atoms are near it in the compound. Okay, so let's say we had C double bond O, bond H, bond H. This carbon-hydrogen bond has a different amount of energy required to break than that one. And why is that? It's because this bit here, which they refer to as the environment in which that CH bond finds itself, the environment, is different than this environment. They're not going to be hugely different, but they will be different. So when you have that chart and it says, oh, CH bonds are always, 436 kilojoules. That's not always true. Okay, that's just an average that they've taken of a whole bunch of different CH bonds And they've said, this is the average. So that's why it can lead to some inaccuracy using bond enthalpies to find the delta H of the reaction. Okay, so if you have a different environment, you get different energies. Okay, so here's just one example of such a thing. Here we have methane, CH4. Now to break all of those H bonds, and this is something they can do in the lab, that takes positive 1656 kilojoules per mole. Okay, 1656 kilojoules per mole. Can I help you? Here. Okay, so we have 1656 kilojoules per mole. Now, it turns out that if we were able to rip off one hydrogen, then the other hydrogens would be held more tightly. So the bond would be stronger. It would have a higher bond enthalpy than in CH4. Okay, so this one has a higher bond enthalpy than CH in CH4. And if we remove a second hydrogen atom, then the same thing happens again. This one would have an even higher bond energy. Now, do you need to know how that happens or why that happens? No. Do you need to be able to explain any of this? No. Basically, the moral of the story is we cannot break the hydrogens off one at a time. We can only break them off all at once. And if we do that, it takes 1656 to break all four. Yeah? So we just say that the average is just 1656 divided by 4. So that is the average energy needed to break a CH bond. Okay, so there we are. I mean, I don't know much more to say because you don't really need to know that. Is okay? But I thought it was worth mentioning because sometimes they ask, why do you get a different value from the bond enthalpies than from, there's this other method you could use, and you could say, oh, because the bond enthalpies are just averages, right? And so it might not be the same bond enthalpy in this specific molecule, okay? But we'll cover that again when we come back to that later on, but it's good to have seen it here, okay? Now, our enthalpy calculations, I'm not quite sure what they're doing here with this little doodad here. What this should say is it should say delta H, and then we have this little 0 up at the top, which stands for not, which just means at standard conditions. You don't really need to know anything about that for now. We will talk more about that later when we do all the rest of thermochemistry. Okay? Because right now, all the things I'm going to give you will be at standard conditions. So you don't have to worry. You can be like, everything is standard. And you're like, what's that little 0 for? It just means at standard conditions. That's all you need to know for now. Okay? So just don't be like, what's that 0 there for? Just means at standard conditions. And because this is a British resource that I stole this from, that's an R, but we're going to call it Hrxn because that's in general how we do it in North America. Okay? So this means the standard enthalpy of the reaction. How do we calculate this? There are several ways that you can show your work. This particular formula, where we have delta H, they put a line through their 0, but this is of the reaction. It's the enthalpy change of the bonds broken plus the enthalpy change for the bonds formed. Enthalpy change of bonds broken, is that a positive value or is that a negative value?
Positive.
That is a positive value, okay? Because remember, if we have bonds broken, we have breaking and entering, yes? Yes? Now, enthalpy change for bonds formed is going to be negative. So that's one way of calculating it. You take all of your bond enthalpies for things that are broken, those will be your reactant bonds, and you make those positive, and then you take all the bond enthalpies of your products where your bonds are forming, and you make them all negative, and then you add them all together. Okay, we've got a couple of examples here that can show you how to lay out your work. There's so many different ways to show your work. When you're doing your work, you know, when I give you some time to work on it, if you're showing it a different way and you just want to check with me and say, is this enough? Right? And I can give you like a little critique on it, like, oh, maybe you should write kilojoules per mole here or whatever. Okay, so you don't have to write it in any particular one of these two ways. Here is another version of that same formula. But what's different in this one is that here, instead of adding everything up, we subtract. Okay, so we keep all our values positive. And we have our delta H of the reaction is equal to, what does this symbol mean? Pardon me? Broken. No. Yes. The sum of. So what it means is it means add up all the enthalpies of the broken bonds. So those would be your reactants. And then you add up all the enthalpies of the bonds formed. Those are your products. And then you subtract. And it works out exactly the same as the other way, because in both cases, everything ends up being negative that is being formed. In one, it's because you make them negative and then you add them. Here, it's because you subtract them. Okay, so here are some relevant bond energies given to us. And we are told here is our Haber process, or Haber process, I don't know how you pronounce it. And it is N2 plus 3H2 gives us 2NH3. Now, they've gone straight to saying how many bonds you have of each type. You have 1 N triple bond N, 3 H single bond H, and 6 N single bond H. But you will be given, for now, the Lewis structures. So you can take a look at them, yes? So let's actually try. I would like you to just attempt to draw the Lewis structure for N2. And you're going to start that by saying, I have an N, and N is in group what? 15. And if it's in group 15, how many valence electrons does nitrogen have? 5 valence electrons. So we have N with 1, 2, 3, 4, 5 valence electrons. And we have our other nitrogen with 1, 2, 3, 4, 5 valence electrons. How many electrons does nitrogen want to have? Wants to have 8, okay? So we need to give each nitrogen a complete octet using only these 10 electrons. So what you're going to have to do is you're going to have to bond them, okay? And I think I'm just going to go over to the right here. And remember that one line, that's a bond, is how many electrons? 2 electrons. So you might need 1 bond, you might need 2 bonds, you might need 3 bonds, and you get to draw a structure. So why don't you give that a try? Not that you're going to have to do that now, but it's worthwhile remembering what Lewis structures are and how they work, okay? So give that a try. See if you can make a structure for N and N that uses 10 electrons and gives both nitrogens 8. Yeah. Got it? Okay. Beautiful. Nice. Nice. Yeah, no, you're good. I think this electrons are stay on there. Okay. Definitely. Yeah. So. Yeah. Excellent. And press down to you. Okay. So, here, this structure has 2, 4, 6 electron bonding electrons.
You can't remember it? And you don't know the difference? Do not understand it. First remember it, because I first I think it takes a little bit of time. Like the rope.
That's the thing.
Rope
What's happening? We're drawing a structure for
and
N
entering.
and N
Rope
together.
on
Forming into.
entering that.
Here's bonds. There are two electrons. There.
The energy from this.
That's okay. I'm sure everyone is there. Okay?
No, potential energy is over here.
Yeah.
And the progressive.
Okay, so we have 10 electrons.
Yeah. There.
So I'm going to show you guys you can just cram these together, and most of you did and got it correct, but I'm going to show you the official method for how to write a Lewis structure that will get you there every time, okay? And what we do is we say, I have 10 valence electrons. I'm going to set that aside for now, and I'm going to draw an N. I'm going to bond it to the N. And then what I'm going to do is I'm just going to give everybody 8 electrons. Okay? I'm just going to use lone pairs and fill everybody up. I'm going to say, I've got electrons like crazy. So many electrons, as many as I want. Isn't that great? Except that I don't really have that many. Yes? So what I do then is I say, I should only have 10, but in this structure, I have 2, 4, 6, 8, 10, 12, 14. So that's no good, right? So what I do then is I erase electrons until I get down to 10. Okay, so I'm going to erase some electrons. Okay, so now we're down to 12. And now we're down to 10. Yes? And now we're like, oh, yay, now I've got 10 electrons. That looks great. The only problem is if I look at my nitrogen, nitrogen has only 2, 4, 6, right? That's a problem, okay? So what we're going to do is we're going to say, okay, well, what if I took this pair and moved it in here so I have a double bond? Yes, so instead of being a lone pair, it's going to become a bonding pair. Okay? And what that's done now is it has said, okay, this nitrogen here on the left now has 2, 4, 6, 8 electrons. Yay! But we're not done yet because who is still dissatisfied? The nitrogen on the right only has 2, 4, 6. How could we fix that? We could say, hey, you shared with me, I'll share with you. Why not? Okay, so now we still have 10 electrons, 2, 4, 6 in the bonds, and then 8, and then 10, but everybody has 8 electrons. The power of that method is that, do you remember when we had all the electrons on that structure at the beginning? When you erase 2 pairs, that tells you you're going to have to turn 2 lone pairs into 2 bonds. Okay, so that says I erased 2 pairs of electrons, so I need to take 1 pair, a lone pair, and turn it into a bond, and I need to take a second lone pair and turn it into a bond. Okay, so that's why I like the fill it all in and erase it method, as opposed to some people will just say, oh, you've only got 10 electrons to work with, don't do that. It makes it harder to see how many double or triple bonds you're going to be forming, okay? Don't worry, we're not doing this now. This is just a preview of Unit 10, okay? You don't need to be able to do this. I will give you the structures. I will draw for you N, triple bond, N, and I'll draw 3 H's, so I'll be like H, 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 H. So there's our reactants. And then our products, we have NH3, NH3. And you'll notice here, I haven't drawn the lone pairs in because it is irrelevant to the bonds. Yeah, I could draw them in if I wanted to, but they just kind of clutter it up because I don't need to know that there's a lone pair here in order to say I have an NH single bond. Yeah, so I will give you this and you will say I need to break one NN triple bond. Okay, so you can do a little table like this. This is one method of showing your work. Method 1. Okay, so you can say I got one NN. And so that's going to be 1 times 945. Yeah, so I go, oh, how did I get that 945? I looked it up. Okay. And 1 times 945 gives me 945. And the thing I like about this method is I can put the unit at the top of the table, and then I don't have to write the unit beside every single number. Because in chemistry, every number should have a unit. But if I put it at the top of a table, it's taken care of. So I don't have to write it over and over and over. Yeah? I also have 1, 2, 3 HH bonds. 3 HH bonds. How much is an HH bond? 436. So we're going to say, okay, I've got 3 times 436 gives us 1308. And then I add all them up, and my total is 2253, and my unit is still given at the top, kilojoules per mole. Okay? And it's positive because bonds were broken. Now in the products, our bonds are being formed. So we are forming 1, 2, 3, 4, 5, 6 NH single bonds. Okay, so we are forming 6 NH bonds. So that's going to be 6 times, we look up our value, 391. So 6 times 391 is 2, 3, 4, 6. But now because bonds are being formed, that's going to be negative. Yes? And again, what do I have up here? I have the unit. We're almost done. In order to get the whole thing, we need to add these two. This whole thing needs to get added together. So that's down here. We have delta H naught of the reaction, and we have our positive 2253 kilojoules per mole. And you'll notice, what do I have in my calculation now? Kilojoules per mole, right? Because no number exists without a unit. And we also have our negative 2346 kilojoules per mole. We add those two up, positive plus negative gives us negative 93 kilojoules per mole. Don't like writing kilojoules per mole? So often you could say positive 2253 plus, oh, actually here, let me put this in square brackets. Plus negative 2346, and I could stick my kilojoules per mole on the outside. So that's also a way to do it so you don't have to write as many kilojoules per mole. Method 2, and I don't know where there's room to do this. There might be room at the bottom of your page. Is there room at the bottom of your page? Oh yeah, it looks like it. Okay, so we have, method 2, you can use this formula, delta H reaction is equal to the sum of H of the bonds broken minus the sum of H of the bonds formed. And then you would say, okay, I have my bonds broken. I have one NN. So this here is going to be one N triple bond N plus 3 HHs minus 6 NHs. So then I'm going to substitute in here for 1 NN. I'm going to substitute in 1 times 945. And then I'm going to have 3 times hydrogen. So that's 3 times 436. Kilojoules per mole. And then we subtract 6 times well, what's the value for NH? 391. 391 kilojoules per mole. And you can throw that all into your calculator and you will still get negative 93 kilojoules per mole. Those are 2 methods of showing the work. There are other ways to do it. If you have one that feels more comfortable to you, please feel free to do it and just come and check with me and make sure that you've got all the stuff you need. Okay? At this point, I think you're probably okay just to work on stuff. So if you have not done anything yet in pages,
Where is it?
pages 119 to 123, those will be a good starting place for you to do some stuff on this. So the homework, pages 119 to 123. But you can also, if you feel like you've done a little bit of that, you can also work on this one, which is also practice stuff, like on more of the more general stuff from 6.4a, b, and c. So this is like endothermic, exothermic, draw the graph, put the heat term in, that kind of thing. Okay. So when I say this, just work on some of it. Yes? So the two handouts. Work on some of it. So work on some of it now, work on some of it after school, like for homework. Do some. So you can decide what you want to start with. You can either start with 119 or you can start with one of these. This one has a few extra problems at the back. They're actually from our big, gigantic textbook, but I've just thrown them in here. Okay, so, and the answer key is from the textbook. So it's done in its own little formatty way where it calls the bond enthalpy D. I don't know why it's D, but anyway. You're going to work on things. You're going to come to me when you have help because I'm going to be marking your quizzes. Maybe I'll get them done before the end of class. Okay, so come up to me when you have questions. Is that good? Okay. Yeah. Let's see. Great time.
Lock in. Maybe I should stand and do it. So I'm not tired. I'm gonna do this one at home.
Oh, and there's a couple things where the answer key is wrong. So I think number 8 on page 122, the answer key is wrong. Page 122, number 8.
Well, you put the right answer on team. Oh, that works.
I'll post it on Teams maybe tomorrow morning.
Okay.
Because I imagine when I get home tonight, like I've got to do some exercise and make dinner and blah, blah, blah. It's not going to happen tonight, but it will happen tomorrow morning.
Okay.
Okay. Number 8. And on the energy changes extra practice.
So this
Oh, and we're having the quiz on this stuff on Monday. Is that okay? Oh, what's happening Monday?
Wait, what is that? Oh.
Is that okay?
You have your physics and
You have your physics midterm
No.
unit test. Pardon me? Oh. Well, you can talk to me about maybe writing it some other time if you need to. Okay? Yeah. Hi. I don't care if we do it on Tuesday. It doesn't matter to me. We can do it on Tuesday.
Yeah, maybe Tuesday's better.
Tuesday's fine. We can move it to Tuesday. Sure, sure. Yeah.
Wait, what about the second block they're doing on Monday?
Huh?
They're doing it.
Well, no, I'll move them to Tuesday as well.
Okay.
It's fine.
What do you have on the weekend? Oh, right.
First performance is a whole event for Sunday, and for Saturday we have.
And the energy changes extra practice, number 1C is endothermic, not exothermic. Okay? I changed the question, but I didn't change the answer key. Ha, 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 ha. Ha. It is what it is. Okay, here we go.